Welcome back to the deep dive. Today, we're zoning in on a region really facing some profound climate threats. We're talking about the Middle East and North Africa,
Right.
ENA.
And when you think Mino, you usually think oil, you think gas,
hmm
wealth.
Exactly. But we've got a study here that flips that narrative completely. It offers a truly shocking conclusion, frankly.
It really does. It's the kind of finding that just changes the economic game entirely.
Yeah.
We're diving into towards sustainable development in the Mino region, analyzing the feasibility of a 100% renewable electricity system by 2030.
Okay, lay it on us. What's the big takeaway?
The punchline is this. For MENA, getting to 100% renewables isn't just, technically possible by 2030. It's actually way cheaper, like over 50% cheaper than just sticking with fossil fuels.
Whoa, okay. Over 50% cheaper. That's a massive claim. We definitely need to unpack how they get to that number.
We do. And first things first, we should mention this is a key piece of research, yes, but it is a bit older now. It came out in 2020.
Right, 2020. Good context. And the methodology matters here, doesn't it?
Hugely important. You have to understand, this wasn't a policy prediction. It was more of a technical investigation. They used the LUT energy system model. It's a linear optimization thing.
Okay.
And they ran what's called an overnight study for the year 2030. So think of it like asking, if we could snap our fingers and build the perfect, most efficient, 100% renewable system today,
Yeah.
based on 2030 cost projections, what would it look like? What would it cost?
So it's like an engineering stress test, investigating the case in principle, stripping away the politics for a moment.
Exactly. It proves the pure technical and economic potential, separate from the real-world hurdles for now.
And the need for this kind of thinking in MENA is just stark. You look at the rising energy demand, population, cities growing.
Yeah, and that demand growth is directly linked to CO2 right now. Back in 2014, something like 51% of CO2 from fuel burning was just from making electricity and heat.
And at the same time, the region is incredibly vulnerable. Extreme heat, droughts, serious water stress. It's happening already.
It is. But here's the paradox, right? The system runs almost entirely on gas, and oil renewables were, maybe 0.4% of primary energy supply?
Tiny.
Tiny. But the potential for solar and wind there, it's almost, limitless. Just massive and untapped.
Okay, so let's get into that blueprint. If you're building this perfect 100% renewable system overnight, what are the key pieces? What generates the power?
Well, first, the study scope was pretty ambitious, too. They didn't just look at electricity.
Oh.
No, they modeled the whole system. Power, yes, but also non-energetic industrial gas demand. And really crucially for MENA, seawater desalination.
So sector coupling, bringing different demands together. How do they manage the geography? It's a big region.
They clustered 19 countries into 17 interconnected regions for the modeling.
Okay. And when the model crunched the numbers, optimizing for cost, what tech came out on top? I guess maybe some concentrated solar power.
You might think so, but the model was really clear.
Yeah.
Solar PV, photovoltaics, and wind power, they were just the most cost competitive, overwhelmingly.
Really? Just those two, mainly?
Yeah. Together, they made up more than 90% of the generation capacity in, all the scenarios they ran. And solar PV specifically was found to be the absolute cheapest source based on those 2030 assumptions, especially the single-axis tracking kind.
So why such a heavy bet on just solar PV and wind? What about biomass or hydro?
Well, they looked at them, but they have constraints,
Yeah.
right? Biomass, for instance, competes with farmland, which is limited. And critically, it needs a lot of water.
Which is exactly what the region doesn't have to spare.
Precisely. And hydropower potential is also pretty limited, partly due to sustainability worries and, again, high costs. So the optimization, it basically just zeroed in on what's cheap, incredibly abundant, and doesn't make the water problem worse, sun and wind.
Okay, sun and wind dominate, but that immediately brings up the big challenge, flexibility. These sources are variable, right? Sun doesn't shine at night, wind isn't always blowing. How do you keep the lights on reliably, 2 out for?
That's the absolute core engineering problem they had to solve. And the study tackled it by looking at 3 different scenarios, basically based on how much the regions cooperate.
Okay, let's quickly outline those scenarios.
Sure. First is the region scenario. Think of it as every country for itself, isolated, independent systems, no trading power.
Okay, silos.
Exactly.
Right.
Then the area scenario. Here, they allow full electricity exchange between all those 17 regions, a big interconnected grid across MNA.
Right, cooperation.
And finally, the integrated scenario. That takes the interconnected grid from the area scenario and adds in those other demands we talked about, desalination and industrial gas, full sector coupling.
Got it. So Comparing the isolated region scenario to the connected area scenario must show some big benefits of that grid, right?
No, it's transformative. It
Yeah.
may be a bit counterintuitive. Connecting the grid actually lowers the total amount of renewable generation capacity you need to build.
Wait, hang on. You connect them and you need less solar and wind overall. How does that work?
Because you get rid of so much redundancy. If, say, Egypt has great sun, but Saudi Arabia needs power at that moment, Egypt can just send it over. Neither country needs to overbuild its own solar farms just to cover every single peak or local lull.
Ah, so you share the load, share the resources, makes sense.
Exactly. And it shifts the type of capacity, too, that fixed-tilt PV, the simpler kind. Its capacity dropped like 90%, moving from region to area.
Wow.
Yeah, because the grid lets you rely more on the most efficient options, like those single-axis tracking PV farms placed where the sun is best, and wind farms where the wind is strongest, and then just shipping the power.
So connectivity isn't just sharing power. It's about fundamentally avoiding building billions in redundant stuff across 19 nations. That's a huge infrastructure saving right there.
That's the core of it.
Yeah.
And you see clear trade patterns emerge. Net exporters like Saudi Arabia, Egypt, Iran, Libya.
Sending power to net importers like the UAE, Kuwait, Israel?
Exactly. That traded electricity was actually quite significant, about 14 to 18% of the total final electricity demand in the area scenario. But the grid only solves the where problem, the geographical variability. You still need storage for the when problem.
Right, the time fluctuations. How did the model handle that?
It uses a kind of hierarchy of storage. For the daily cycle, daytime solar peak versus evening demand, it relies heavily on battery storage. Batteries pair really well with PV for that short-term shifting.
Makes sense. What about longer term? Storing summer sun for winter, for example. Seasonal storage.
That's where power-to-gas, or PTG, technology becomes really vital.
Explain PTG quickly.
So PTG takes surplus electricity, mostly from wind and solar when generation is super high and cheap, and uses it to create synthetic gas like hydrogen or synthetic methane. You can then store this gas, potentially for months, maybe using existing natural gas infrastructure.
Okay, so batteries for daily, PTG for seasonal.
Yeah.
Now, here's a fascinating point. Did connecting the grid reduce the need for all this physical storage, just like it reduced the need for generation capacity?
Yes, dramatically so, especially for the bigger, longer duration storage options. The grid connection slashed the required capacity for things like large-scale batteries and adiabatic compressed air energy storage, AAC.
Yeah, storing energy in compressed air underground. Its capacity dropped almost 100% when going from the isolated region scenario to the interconnected area one.
Wow. So cooperation, that grid, is basically the cheapest form of large-scale storage.
In effect, yes. It smooths out so much variability across the region that the need for expensive, long-duration physical storage just plummets.
Which brings us to the grand finale, the integrated scenario. You've got the interconnected grid, and you couple it with desalination and industrial gas demand. What's the final impact on the economics?
This is where the system really hits peak efficiency in the model. Adding those other sectors, coupling them in, it dropped the total levelized cost of electricity, the LCOE, by another 17% compared to just the interconnected power sector alone. Okay, LCOE, that's the standard measure, right? Total lifetime cost divided by total energy produced. So integration makes the electricity itself even cheaper.
Correct.
But wait, if you're now supplying industrial gas demand too, doesn't that mean the need for that PTG capacity must just explode?
It does. PTG capacity shot up by, get this, 1,820% compared to the area scenario.
That's saying 100%. Wow.
Yeah, because PTG suddenly has this crucial dual role. It's not just providing seasonal energy storage anymore. It's also the factory supplying the gas needed for industry. It becomes this incredibly efficient way to use that synthetic fuel infrastructure for two vital jobs.
Okay, so let's get to the bottom line then. Across these optimized 100% renewable scenarios, what was the final LCOE range, the cost per megawatt hour?
The range was between 40.3 and 52.8 euros per megawatt hour across the scenarios. And that fully integrated scenario, the most efficient one, hit the lowest cost. 40.3 euro NWH.
40 euros per megawatt hour. Okay, let's pause there, because this is the number that just shatters assumptions. How does that compare to sticking with the current fossil fuel system, the business as usual?
Well, the study calculated the BAU LCOE range as well. And even without factoring in costs for carbon emissions, sticking with fossil fuels costs between 118.6 and 149 euros per megawatt hour.
Okay, let me repeat that. Sticking with the old way costs up to nearly 150 euros per megawatt. The fully integrated renewable system costs 40.
That's the finding.
That's not just cheaper, that's an economic demolition. The renewable system is 55% to 69% less expensive. That's an unbelievable financial incentive, isn't it? Especially for countries whose budgets depend on fossil fuel profits.
It's a powerful economic argument. And remember the sector coupling. That integrated approach also tackles the region's most critical vulnerability, water.
Ah, yes, the desalination aspect.
Right. By powering seawater reverse osmosis SWRO desalination plants with all that cheap renewable electricity, the study estimated the levelized cost of water, the LCOW, at about 1.4 euros per cubic meter.
And what does 1.4 euro mean practically? Is that affordable?
It's basically comparable to the cost of fresh water produced today using fossil fuels, which is often heavily subsidized. So you get sustainable, clean water security at a similar price point. But without the pollution and without needing those massive ongoing subsidies, it fundamentally changes the water outlook.
So this study, towards sustainable development in the MENA region, analyzing the feasibility of a 100% renewable electricity system by 2030, it really lays out the techno-economic case, doesn't it? Feasibility seems proven, driven by cheap solar, cheap wind, and that crucial grid cooperation.
The numbers are hard to argue with, technically and economically, but the study is also careful to point out that just because it can be done doesn't mean it will be done easily.
Right, the real world intervenes, the politics.
Exactly. You can't ignore that many national budgets and, frankly, regional stability are deeply tied to selling the very fossil fuels this model suggests phasing out domestically. That's the paradox they have to navigate.
So the engineers show the path, but policymakers need to figure out how to handle those tricky transition issues, national interests, fossil fuel revenues, social acceptance.
Absolutely. But the study highlights powerful co-benefits that should help push things along. We're talking huge job creation in new industries, much-needed economic diversification away from just oil and gas.
And freeing up more oil and gas for export, potentially, making more money from it that way.
That's a key point, yeah. Reduce domestic consumption, export more. Plus, a massive reduction in the cooling water needed compared to old thermal power plants. That's a huge win in a water-scarce region.
Okay, so let's end with a forward look. If MENA actually pulls this off, builds this 100% renewable system, what's the next step? How does this change their global role?
Well, they don't just solve their own energy needs. With that practically limitless renewable potential, they could become a new kind of energy superpower.
Exporting electricity, you mean?
That's part of it, sure, exporting power via new interconnectors. But think bigger. They could use that ultra-cheap clean energy to produce green hydrogen or synthetic fuels for export decarbonizing global shipping or aviation, for example.
Ah, value-added energy export.
Exactly. Or even offering services like direct air capture and storage, using their renewable energy and geology to pull CO2 out of the atmosphere for the rest of the world. That solar resource isn't just regional. Deployed at scale, it's a global climate solution they could potentially export.
A fascinating vision, moving from a fossil fuel exporter to renewable energy and climate solution exporter, grounded in some surprising economics.
Indeed.
Well, that deep dive was based entirely on the 2020 paper, Towards Sustainable Development in the MENA region, analyzing the feasibility of a 100% renewable electricity system by 2030. Thanks for joining us.